Welcome back everyone. In the previous session we covered PCA, and later on we covered the application of PCA into the project wine that we did, breaking down to two components, principal components. We also figure out how to actually select the right number of principal components to use in order to achieve a certain level of variance that is being accounted for. So that's pretty much where we are up to. In this session, I want to cover a little bit, a slightly different angle. Whenever we're actually dealing with anything that's non-linear, we're going to have some challenges with the linear PCA that we've covered. So in this session, we're going to go into looking at non-linear, dimensionality reduction through the use of the kernel. And let me just start with this. This is the actual documentation at scikit-learn, as well as the reference. I'm going to leave that with you for now, but the main point that I really want to illustrate is how the actual kernel PCA works. So for a start, what we want to do is actually from scikit-learn, from the data sets itself, it does actually have this really interesting so-called, I guess you could call it functions that they're built in. It's called make circles, whereby scikit-learn data sets import mix circles. All right, we're going to make use of that to create circles so that we can use the PCA and to actually to extract the relationship and to decompose. All right, so let me import the actual libraries, decomposition, import PCA as well as the kernel PCA. All right, that's all good. So now we want to actually set our random. I do need to import numpy as np, and also import pandas as pd and as pd. All right, okay. All right, so the next thing is we're going to generate some random numbers. I'll just set the seed to 0 so that you actually have the same observation as me. And the next thing is we're going to generate x and y, and this is where the make circles part comes in. Make circles, we're going to set the number of, now before I run off doing that, let me just run the so-called documentation. So this is making large circle containing a small circle in 2D. So it's basically a toy data set to visualize clustering as well as classification. Now, what we're going to do here is setting it, one of the parameters you need to put in is number of samples. Instead of 100, I'm going to make it a little bit denser for 400. And the factor is 0.3. What is the factor? Okay, so the factor here basically is scale the factor between inner and outer circle. So that's pretty much what factor is. And the noise is 0.05. So as a standard deviation of Gaussian noise added to the actual data itself. Okay, having done that, so let's run that. Okay, so the first thing now that we really want to actually see is what does this visually looks like. Okay, and let's plot that out. I think before I do that, I just need to import matplotlib.pyplot as plt and matplotlib inline. Okay, let's squelch that. So this is what it looks like, okay, in terms of the two circles that we made. Remember the descriptor or the documentation said you make two circles, all right, so two small circle in 2D. Now the part that you probably weren't too clear of is why did I actually choose a factor of 0.3? So let me, what does that actually have any bearings? Just now it's 0.3, now set to 0, and this is what it looks like. So what happens if it's 1? Okay, you can see the difference now. So that is basically let you see how closely the two circles overlap. Okay, so when it's 0.3, basically they hardly overlap. The actual gap is very, very large. So okay, now having done that, so let's keep going. All right, now we're gonna make use of the kernel PCA. Now, no doubt when you look at this, your linear PCA is gonna have a lot of difficulties. So what do you do? The PCA is gonna chop this way. It's not gonna work. It's gonna completely fail in this task to actually identify the principal component in this. Because you just look at it, it's linear, it's non-linear. It's so that's why your normal PCA is gonna struggle. So what we're gonna do now is we're gonna instantiate the kernel PCA and just oops. Now we already import kernel PCA. Yep, and the kernel is RBF. You can choose others, but for now we just need RBF. Fit inverse transform is equal to true, and finally gamma is equal to 10. Alright, so again, let's have a look at the documentation so that you know where I'm going with this. Alright, now the first thing is that it's asking how many components. We didn't state this, the default is none, as we did with the linear PCA. The kernel is actually default to linear, which is not what we want to do, because looking at the relationship we can clearly tell that it is not linear at all. Gamma is set to none, but we set to 10. Why is that? So let's have a look at gamma. Gamma here basically is the kernel coefficient for the RBF and poly kernels. Okay, now you might ask me, how do I choose what gamma? The answer is it's hyperparameters. You actually have to tune this. Just randomly selected a number. You can try it with other numbers. It will work better, or it will work worse, or it doesn't work at all. You know, so this is one of those things that I don't have a straightforward answer. It's just one of those free parameters that you can actually tune. One that you actually have to tune to actually make it work better. All right, so keep that in mind. So having done that, the next thing that we want to do is actually transform PCA, the x-axis, okay, PCA, and fit transform the x itself. Yep, and we're gonna want to get it back. All right, so we are transforming it, and then we are actually extracting out the actual principal components. Now we did this exercise in our previous class. I'm sure you remember the linear regression. Okay, let me actually just pull it out. This is the figure that I wanted to show you. This is in the principal component analysis lesson. Now you will remember this scatter plot, whereby the green line is the actual principal components. We transform we apply PCA to all the scatter plots, and then we inverse it out. When we inverse it out, all we get is just the actual pure principal component itself. We basically all of the variability has been dumped or just left out. So that's what this process does. First is transform X and store it into XKPCA. And then the next thing is inverse transform XKPCA and store it back to X back. But the X back is going to be different from X, because that's just the pure principal components left. Okay, so having done all that, we're going to PCA. All right, instantiate PCA, and the XPCA is equal to PCA, and then fit transform X. All right, so this is for comparison purpose. All right, now that we've done that, let's plot this again. Okay, so plot figure, and we're gonna set the title, called the original space, and we set reds is equal to y equal to 0. Okay, so what does that do? When y is equal to 0, reds becomes 1. Whereas for blues, when y is equal to 1. Okay, now this is the part that you're probably a bit confused. Let me just have a look at what is what type of date. Okay, it's a NumPy array. So what I'll do is that I'll just change this to panda series, and then value counts, so that you can actually see. So we have 200 0 and 200 1. What we want to do is paint the 1 blue, or paint the 0 as red. So that's really what this is doing here. Okay, now let's just plot the scatter. Now instead of calling it 0, we call it reds, because we're gonna distinguish the reds being reds, the blue being blue. Okay, and reds 1, and the color is basically gonna be red. Size is 20. The edge color, we're gonna make it black. Color is equal to black. That's what K means. Okay, that's the first one, and we're gonna plot the second one. Okay, I'm too lazy to type it all. So instead of reds, we want to change this to blue, and then blues again, and blues again. All right, and leaving the rest. Okay, now we're gonna plot the X label. Okay, the notation X underscore 1, small x, and the Y label X underscore 2. I'm gonna just make this 10. Okay, right, so that's pretty much what we want to do. Let's plot that out. Okay, we've got an extra bracket here, and what does it say? It says long list of stuff. Invalid RBG. Okay, I think I had a typo here. K1. Let me see. Where did I miss? Okay, let's run that again. Well, I don't know what happened there. I think it just have some extra space. So what happened if this is 20? Does it look better? Okay, ever so slightly. But what I do want to do is come back here and just change this. Import, not here, I'll just do it here. So import, we missed out on importing one library, Seaborn, as SNS set style and white grid. Okay. Okay, notice the difference in terms of the shape and size. It's a lot easier to visualize now. Okay, now having done that, what we're going to do next is actually plot the principal component itself. So let's just copy this whole thing and put it here. Okay, so now we don't need all of these. Okay, what we want to do now is plot the PCA. Okay, and also the PCA red, and again change this part to the PCA and this part to PCA. Okay, and now we're going to label the title, and the title will be called projection by PCA. So remember, this is the linear PCA, and then this would be the first principal component, and then we have the second principal component. Okay, now that we've done all that, let's plot it out. Okay, I'm really not having a good typo day. Okay, so when you actually look at the PCA, when you actually draw it out, nothing much comes through. You can see that when you actually fit it in, and it basically nothing. It really wasn't able to actually notice that XPCA was fit transform. It just wasn't able to actually extract any relationship out of that at all. So what we do now is have a look at and compare and contrast this to the KPCA. Okay, KPCA, and finally KPCA here. And we're going to call this KPCA because it's kernel PCA. Now the first principal component, and we're going to call this in space induced by the okay, let me just type this out, phi phi. Okay, there you go. Notice that because the of the kernel nature of the PCA, it actually project this, instead of a two-dimension space, it projected into not quite a three-dimension space, but it actually push a space in to actually segregate the two. You notice clearly now is that instead of looking at it from top down, in a way looking like it's from top down, it actually has split it into two sides. You notice that it's been pushed up, and also the other circles was actually pushed down and segregating the actual space itself. I hope that has been useful. That's really an introduction portion to the kernel PCA. When we come back, I'm going to demonstrate this to you in an actual data set itself. Thank you for watching. I really appreciate you.